This is John Black, Super Chemist. My channel is John Black, Super Teacher. I want you to remember this list here. You know, the right side is righteous; they're positive. Left side is sinister; they're negative. You know what I mean? Now we were talking about acids before. There's two things that each side of these lists can do. Right? These are positive people, so they're either going to give you money, meaning protons, or they're going to take a bill from you. Right? That's the two nice things it can do. What are the two terrible things this can do? It can accept the money, accept the protons, or it's a terrible person that likes to give its bills away to other people, so it will uh, give electrons, right? Now, we discussed last week an Arrhenius acid is the proton type of acid, okay? It gives money. It gives protons. If it's in aqueous solution, it's considered Arrhenius acid. If it's not in, because you go through a hydronium intermediate, the proton jumps off the acid onto the water and makes hydronium, and that's what does the reaction. If there's no water, then you'd call it a Bronsted-Lowry acid. But both of them are giving away. They have nothing to do with accepting electrons. They're giving protons away, or they're giving money away. Now we're going to go into the third type of acid, a Lewis acid. It deals with electrons, okay? So a Lewis acid accepts electrons, and remember, we don't have to memorize what a base is because it does the opposite. If this accepts electrons, then this has to give the electrons, right? I want you to notice the easiest Lewis base is water. See how you got your two waters here, and then you have your lone pair electrons sticking out. And that's one of the main things you need is lone pairs, right? To be a Lewis base. But to be a Lewis acid, it's the opposite. Now here's an example of a Lewis acid, right? It's this example, most examples at first will be trigonal planar, which means it's got this little Y thing. These are all in the same plane. And then this bubble goes up above like this. This would be the bubble. Or this would be the orbit, right? You have an empty p orbital here. Just because it's empty doesn't mean it's not there. It's still there, right? So let's say you have this entity here, right? And I want you to notice the trigonal planar, that's the third A3 group on the periodical table, right? On a periodical chart. That means it has 3 electrons. It gave one here, and one here. But it has this empty p orbital, right? I want you to notice this is ammonia. Everyone knows ammonia, right? NH3O, right? NH3. And it, again, it is on the other side of carbon. So instead of being in the 3 slot, it's in the 5 slot. So it gives away 1, 2, 3 electrons. Oh. And then it's got these other 2 electrons because it has 5, right? 1, 2, 3, 4, 5. And this can go back and forth. This is the same orbital. This is the same orbital. But look what happens when they get close together. You got your LUMO, your lowest unoccupied molecular orbital, and your highest occupied molecular orbital. What's going to happen here? You got electrons and you have an empty orbital. Well, they're going to form a bond. And when one entity gives 2 electrons to form the bond, because you notice in these bonds, the nitrogen gives 1 and the hydrogen gives 1. The boron gives 1, the hydrogen gives 1. Oxygen gives 1, the hydrogen gives 1. But in this bond right here, both electrons are coming from the nitrogen. So it's considered a dative bond, an adduct, a coordination complex. This is your acid. This is your base. This accepts these electrons. This gives these electrons away. It's that simple. Now I want you to notice one of the most, it's the first Lewis acid that you'll come in contact with. And like I said, it's going to be trigonal planar. Is in the Friedel-Crafts acylation or alkylation. In this case, we're doing alkylation because we have an alkyl group here. That's what R stands for, any random group. of hydrocarbon. Now you'll notice that this is negative, okay? You might say benzene isn't negative. You're right, it is not negative, okay? It's neutral overall, but because of all these double bonds, you have a very high electron density, okay? And sometimes the density is more on one side, more on the other, and you end up with a negative charge, partial charge on one side of the benzene ring, right? So there's your negative part. We know there's only two parts to any reaction, a negative and a positive, right? Well, we want to add this alkyl group to here. This is very electronegative. Alkyl groups are very weak, very, they're not strong. They can't. This chlorine is so electronegative. Remember, it's on the right-hand side of the chart. It wants to take electron density. It wants to take something negative from you, right? So it does induce a slight charge dipole on here where you have more negativity here, more positivity here. But for this to react, there's not enough difference in charges, you know what I mean? This positive and this negative are not enough far apart that they're going to have that they're going to want to react, okay? So you need a Lewis acid for this reaction. This is your Lewis acid. You can use iron chloride or aluminum chloride. There's a couple of things you can use. I chose this one because it has the trigonoplanar and it's nice and simple. It's in the third row, just like boron. So you have your same trigonoplanar, your same p orbital. Now when this gets next to this, look at this. You got your lone pair electrons and you have an empty orbital. What's going to happen? The same thing is up here. This electrons are going to jump into that orbital and make an adduct, make a dative bond. Sometimes the R will come off and be positive, and this will be negative. Sometimes it just stays like that. But that's okay. It doesn't have to actually come apart, because since this chlorine gave up some of its electron density up here, right? And this is powerful. This wants that electron density. So chlorine, he gave up 2 of his electrons to share, right? What's he going to do? He's electronegative. He wants negativity. And he just gave some away to this big boy here. So who's he going to do? He's going to pick on this little scrawny guy, right? He's going to take some of his electron density. So now, not only is this positive, it's more positive, because up here it was positive a little bit. But now since the chlorine gave away some of its electron density, it's trying to get it back. And it can't get it back from this powerful big boy here. It got to go for the weak guy. He's a bully. He's just going to take it. So now look what happens, right? Electron density comes out, grabs this R. The chlorine, he's happy to have this extra electron. So he grabs it because he's electronegative, you know what I mean? And what do you end up with? You end up with an alkyl group on your benzene ring. Now this ain't what the video is about, but I might as well put it in. This is actually a bad reaction because, one, this is more reactive than your starting material, and you end up over-alkylating. You end up putting more R groups, more alkyl groups on here to over-alkylate. The other thing is if you have like if this R group was this, if you have an R group like that, see how there's it might come out like this, because you'll have rearrangement. Okay, so it's kind of Friedel-Crafts acylation is a lot better than alkylation. But anyways, that's not what this video is about. The last thing I wanted to go over is these are your basic types of Lewis acids. I don't expect you to understand all of them if you're a beginner, but maybe in the future you might want to come back to this and look. Trigonoplanar species like BF3, carbocations, this, BH3, aluminum chloride, they're examples of trigonoplanar. Oxonium ions, you might say, what's that? It's just basically a positive ion, like hydronium, H3O, oxonium, ammonium, a lot of people know ammonium. See how the end it says onium. High oxidation state transition metal cations like As we said, this can be iron plus 3 chloride. You can see right there. Also, other metal cations like lithium or magnesium plus 2, often as their aqua or ether complexes. And that just means that all the surrounding dative bonds, all the coordination, all the ligands are water. And in this case, it'd be all the ligands are ether in that coordination complex. Electron poor pi systems like enones and tetracyanoethylenes. Now that one, I don't expect you to understand that. Don't worry about it. Pentahalides. That just means pent 5. Halides means like chlorine, fluorine, bromine, iodine. But you have 5 of them attached to a phosphorus or an arsenic or an antimony. That will, those are all examples of Lewis acids. So remember that this type of acid is the only one that deals with electrons. The other 2 acids dealt with the acid giving positive protons, whether it was in water to a water molecule and then did the reaction, or there was no water and you just gave a proton to another molecule. This one deals with electrons. Lewis acid accepts the electron just like here, and the Lewis base gives the electrons. And these are just a couple examples. I mean, I'm not getting as much into it as I should, but this is a beginner's video. And always remember, an acid is popular. Everyone knows what an acid is. No one knows what a base is. So an acid must be the positive one, right? And if it's positive, if it's on the right side of the list, then it's either doing something good. And the only good things you can do in chemistry is give someone some positivity, some money, some protons, or to take away their bills, take away something negative like electrons. Yeah, base is garbage, you know. Nobody knows what a base is. You know why? Because they're garbage. They're always doing something nasty. They're not popular like an acid. They're always trying to give you bills or take your money. No one wants to hear about a base, but everyone knows what an acid is because they're popular. They're good. They're righteous. So you all have a great day, and always remember, science is great.